everybody. If you didn't see my talk yesterday, my name is Meaghan Fitzgerald. I'm a DevRel engineer at Avalabs. And today I'm going to be talking about Avalanche's native interoperability protocol. It's called Avalanche Interchain Messaging. So I like to put into perspective first, like how many people here have run their own L1 or Subnet? Hell yeah. That's the engineering team, so they better have. But anyway, there's many ways to measure blockchain performance, but for the purposes of this presentation, I think we're going to focus on two. So the first thing we think about when we think about blockchain performance is throughput. How many transactions can effectively be sent in conjunction with each other at the same time, processed quickly, and provide like a positive user experience for people who are using blockchain applications. So, our chief UX designer, Martin Eckhart, JK, he's DevRel engineer, made like a really good analogy that he likes to think of blockchain as a highway and how many cars can drive quickly to their destination on this highway. So the throughput is kind of like the wideness / like the efficiency of the road, and then the time to finality is how long it actually takes them to get from the start to the end of the road. If you look at Avalanche, Avalanche already performs very, very well compared to other blockchains. We have kind of this really wide highway, a high throughput, and obviously a short time to finality. That time to finality varies by chain, but on the primary network, you can see a transaction finalized on the C chain within seconds. Bitcoin obviously pioneered the industry, but we all know that the transactions on Bitcoin can sometimes take hours to reach finality, and Ethereum kind of sits in the middle. But the engineers at Avalanche have always kind of understood that no matter how hard they work, that they're never going to be able to make a highway wide enough for all the applications that people want to run on blockchains. And to assume that one blockchain could handle the load of every application running on like the internet perhaps is kind of something that we think is not necessarily logical. So Avalanche has obviously created the ability to create your own chains, your own L1s, and we get this massive combined throughput, multiple highways because of the ability for people to launch their own chains specifically built for their applications. But this kind of creates fragmentation. So like if you have multiple chains, even if they're running on the same network with similar like consensus protocol, the state that is stored on each of the chains is fragmented. So we always knew that it was really important to build native interoperability into the protocol so that the chains could interoperate with each other, and applications that need to access resources on the C chain perhaps or on another chain have the ability to do so and don't have to worry about deploying and managing that infrastructure themselves. So when you think about cross-chain communication, if you've ever used a bridge before, it's a very arduous process. It has a lot of steps, but in order for us to safely communicate cross-chain and make sure that actions on chain A and actions on chain B are like cryptographically verifiable and undoable and everything like that, which I'll get to in a while, you have to ensure that the message that you send from source chain to destination chain includes a proof that the event actually occurred. If you're just assuming that messages from some source are always going to be truthful, that can end up being very bad for you as an operator in the future. So interchain interoperability is super useful for things like asset bridging, DAO voting across chains, cross-chain liquidity pools. Like I think one of the biggest talking points that our BD team usually has is that they like to talk about how if you deploy your own L1 on Avalanche, you can already have access natively to the liquidity that exists on the C chain and all the DeFi protocols there. So in order for us to have a useful and effective interoperability protocol, like the first thing you really have to think about is security, which the blockchain trifecta is like security, speed, and performance. This is like the pillar, the essential part of this protocol. And you would expect that everything considered here would slow down, but the cryptography schemes that the team chose to implement for ICM actually are pretty performant and very fast. I'm going to show you soon. So necessary properties for secure messaging. If you went to school for computer science, I hear you probably learned about this in your cryptography course, but the first thing that you need for secure messaging is authenticity, which just means that the message sender is known, confirmable. You have no doubt that the message source that says where it comes from, is from the person who sent it. Then you have to have non-repudiation. Non-repudiation is basically that the message you have received and the actions involved with that cannot be revoked or canceled. Once I sign a message and decide I'm going to send this action from my chain, I'm going to call a function on the C chain from my L1, that action cannot be undone. I can't decide to undo that and then duplicate my funds on both chains. And then integrity, that means that the message cannot and will not be compromised. Once I sign a message and decide to send it somewhere, nobody else can tamper with the contents of that message. So signing messages, ICM basically takes advantage of the ability to sign messages to ensure that all of this is. Like the signature wraps the message and basically provides these 3 pillars of security for each of our messages. They can't be undone. The sender is who they say they are, and they can't be undone. The sender says who they are, and the message cannot and will not be compromised by any third parties or bad players. So there are 3 signature schemes. So ICM implements something called BLS. I actually don't know the full name of BLS, but I know BLS signature schemes, they're really powerful. They were created by some researchers at Stanford, so we cannot take credit for them, but we did love implementing them. So the first thing you can do is with any cryptography like protocol, you can generate keys. You can generate a secret key and a public key. It's the same way that you generate your Bech32 address on a UTXO chain, et cetera, et cetera. This is just BLS signature schemes though. Then you can actually sign any message and with your secret key, which encodes it in a way and also makes it so that aspects of that message are always reproducible with the verify. So if you know the message that has been sent and you know the public key of the sender, you have the signature, you can call the verify command and it'll return true or false to basically prove, yes, the person is who they say they are, the message has not been tampered with, and the message will not be undone. So BLS signature schemes are actually really powerful because you can implement multi-signature schemes, and the reason why this is important for Avalanche and for L1s is that you don't want one validator to sign a message and send it someplace else saying, this happened for sure, and I'm gonna, like, the state exists on the chain as such, and this person wants to perform this action. If only one of the entire set of validators of a chain sent that message, they could just say whatever they wanted, and like people would have to believe them. Multi-signature schemes unlock this power where if you have a network of multiple nodes, at least a threshold of a certain number of those nodes sign that message in bulk. And basically you have the trust of the entire network of nodes, and there's not really a lot of incentive for those nodes to behave maliciously, right? Like it would be a lot harder to what's the word? Like basically congregate and decide that they're going to send a malicious message. But for example, like you can wrap a message with a signature of at least 7 out of 10. It's the same way that if you've ever interacted with like a Gnosis safe to set up a multi-sig wallet so that only an action can be performed if a group of people decide to perform it. This is similar to that, but we use BLS signature schemes instead. Now this can actually you would think that this would actually get really bad, because if you just want to send a short message that's about 64 bytes and the signature produces the message and then sends it out as 48. If you have a network of 1,200 validators and you need at least 1,000 of them to sign that message would end up being like 48,000 bytes, which is really inefficient and very ridiculously large for a message that originally was only 64. But BLS signature schemes actually have signature aggregation, and they also have public address aggregation. So you can basically request a signature from each of the validators for the message to be sent. And then you can take all of those signatures and reduce them down to 1. So this may be a bit confusing because of the way that it's set up, but the way that BLS signature aggregation will provide security for ICM messages is that you take all the signatures of the validators, you aggregate that, and then you take all the aggregated public keys, you take the message that the validator or that the chain is trying to send, and you input them all into that original verify function. So it's the same function I showed you earlier here. You just have a single public key, a single signature, and a single message. And you can verify that that is true, it's non-reputable, and that it's ensured by the entire network. So it's a really powerful protocol, and I think that it was probably one of the best decisions the engineers made during the Banff upgrade. So signing messages for cross-chain dApps can exist at every layer, and ICM actually is the basis. This is just an arbitrary byte messaging protocol. And what that means is that you can send like messages, which are just a string of bytes to and from other chains. But if you want to interpret those bytes and use them in like smart contract applications, you need a standard interface for interpreting those actions. This is basically like, we send a very short message, but if you don't understand how I created that message in the first place, you won't be able to understand what the message says. Kind of like a cipher a little bit. So ICM is the basis, but our team has also created an EVM to EVM protocol called ICM contracts, which is a standard interface for interpreting bytes across EVM chains. Our network has a lot of EVM chains because we maintain a fork of the EVM called Subnet EVM that most of the layer ones deployed on our network integrate. So I'm going to talk more now about the ICM messaging protocol and why it's so powerful and how it's actually implemented on our network. And this is still going to be kind of focusing on the protocol itself, and later on I'll get to the contracts. Doing good on time. So ICM is really powerful, and BLS signature schemes are taken advantage of on our network because the P-chain acts as the validator registry. Going back to the common themes we've heard about this week with Avalanche 9000, the removal of the requirement to validate the primary network has unlocked the ability for validators to run faster, more efficiently, and cheaply, but they must still sync the latest block of the P-chain because in order for them to interoperate, they must have access to the public keys of all the validators of all the other sets. So whenever a new validator comes online to start either validating the primary network or an independent L1, they have to register a node ID, a BLS public key, and they also have to register their weight for like consensus purposes on the chain. But we're going to mostly focus on the public key. These are the same keys that will be used as a reference for that verify function I said earlier. It's how the relayer that is relaying the messages between the chains will be able to decipher those messages that are sent and verify that the source of those messages are accurate and not reputable. So ICM message signing basically from end to end happens like this. The P-chain provides the relayer with a weighted validator set of the source L1. And then a subnet decides, or an L1 decides, I want to send a message to another chain. So they send a message to the relayer, it's unsigned. The relayer will go to the P-chain, look up these node IDs, the BLS keys, and then they will produce a valid signature from that subnet. They will aggregate the signature together. So it'll get individual signatures from each of the validators. Again, at a certain threshold, each L1 decides what they want their threshold to be. And then they will send a message to the destination chain with the aggregated signature. So they'll get every single individual signature, and then they'll smush it down into one. Then that same relayer from this slide will go to the destination L1, and they will submit the message as a transaction on that L1. The aggregated signature will be verified by the validators of that chain by referencing the P-chain, which is always up to date with the valid BLS signature, the valid BLS public keys. And then so long as that verify function returns true, the message will be executed on that chain. So this seems like a lot. I'm a Solidity developer. I mostly do front-end stuff, and like I use WAGMI once in a while. So like, why do I have to know what all of this is about? And the good news is that you really don't. If you're familiar with Teleporter already, we renamed it to ICM contracts just to be a bit more concise. Marketing, shout out to marketing. But the message flow that I just described from end to end, from dApp to dApp, like kind of looks really convoluted. But as a developer, you actually really only have to pay attention to the ICM contracts interface, and then your Solidity smart contracts that you've probably already deployed. ICM contracts is basically just a bunch of interfaces that have been completely audited by a predominant auditing firm in our industry and are implementable as interfaces in any other standard Solidity smart contract. So when you are interacting with AWM and using this really powerful cryptography scheme to like send verifiable messages cross-chain, you actually don't really have to understand how it works in order to effectively use it. And that's because we have, like, again, the interface, which includes a bunch of other functions, but the main function that we focus on here is send cross-chain message. It just requires that you provide the destination ID, the address that you want to send the message to. So that's if I want to send a Vox from my L1 to Michael's L1 to his wallet, that would be his wallet address. And then, or that actually might be, it could be a smart contract, it could be anything. This is fee info for if you want to, if you want your message to be delivered faster and you're using like an open source relayer, you can provide more fee info, gas limit, and then the ABI encode of the message. Basically, it's a standard way to encode and decode messages sent on EVMs. So you can implement these already like built out functions within your contract, or you can implement a contract alone that your dApp communicates with in order to send those messages cross-chain. And then another smart contract on the destination chain will receive the message if they've implemented iTeleporter receiver. They'll get which will be a function that takes the relayer will provide the origin chain ID, the origin sender addresses, and that message decoded. So again, it's like most of the work for the interoperability has already been done for you. The only thing that you would need to do as a dApp creator on your own L1 is implement these interfaces in your smart contracts. And for example, I feel like this is a very simple example. You can call the send message function with the message to, send it cross-chain, and then the receiver contract will receive it and perform some action such as adding to a balance. It's very simple, and the developer relations team has also made so many examples of this online, so I'll provide that at the end. But the last thing I want to get to, with keeping in mind that I want to leave time for questions, is that I think this protocol is very impressive because of the way that it opposites trust away from this like centralized party. Like traditional bridges just require that you have like really strong relationships with like bridge deployers and providers. You have KYC'd them, you have gotten to know them. It's not like trustless, and it doesn't really mesh well with the whole vibe of the blockchain industry. Whereas I feel like the load considerations, I'll get back to this, I want to stay on my original point, but there was a paper that was made a big statement that cross-chain communication is impossible without a trusted third party. But in terms of ICM and ICM contracts, the trust assumptions are that the P chain, which is insured by the entire network, is accurate and hasn't been tampered with. If somebody was able to publish a false BLS key or like somehow like compromise the P chain, that would be really impressive, and Steven would definitely be interested in that, but I don't think that's really a very easy feat. And you only have to trust that the chain you're interacting with is trustful. So like if the chain you're interacting with has thousands of validators, then you can be pretty sure that there's not any funny business going on to try to interact with the chain. Like it's not just a single bridge that you have to trust. You trust the entire network, including the entire network of Avalanche. So I'll go back to that slide earlier. This protocol actually doesn't put a lot of like extra load on the network. It doesn't put any load on the primary network. The primary network does not have to do any actions in regard to ICM. It's just someone else, the relayer is calling like a read on the P chain to get those public BLS keys. The source subnet has a validator sign messages. The relayer does the signature aggregation and the actual encryption of the message. And then the destination subnet is just verifying that the signature is valid by looking those BLS keys up on the P chain. So it's a pretty lightweight protocol. It's had a lot of work put into it to implement it well. And if you want to learn how to do it yourself and actually go through the flow of executing a message send, you can go to the Avalanche Academy, where we have very, very many tutorials on how to do so. Something as simple as just sending an arbitrary message to calling a smart contract on another chain. So I do think I got to the end here. Oh, this is my socials. If you want to connect with me or ask me any questions now, we have about 5 minutes. But if you would like to text me, if you get to this next week, if you get to the tutorial in a month from now and you have a question about how it works, you can just message me on Telegram. I have everything that associated with me there. LinkedIn, I think I got some, I don't know, coupons up in there too. It's like a weird website. But anyway, we have about 5 minutes. So are there any questions about anything I talked about? Yes. Can somebody give him a microphone? I'm the MC for this one too, so I could do it. Thank you.
Thanks. You had are you able to go back to the ICM message delivery slide? I'm just trying to help my understanding of something.
This one, or do you want to go to this slide?
I think it was titled ICM delivery. Yeah, around here.
Yeah.
So it's the relayer that's aggregating the signatures, right?
Mm-hmm.
But where does the aggregation of the public keys of the source chain validators happen?
So that's actually happening in the relayer. I think
the relayer is also aggregating the public keys as well as the signatures.
So the relayer gets the public keys, and it actually produces that signature. So what you're describing to me sounds like the same process. So
okay, but for the verification, right?
Mm-hmm.
They need the aggregated public key,
Mm-hmm.
and they compare that to the aggregated signature.
Mm-hmm.
So I'm wondering where the aggregated public key is produced. It's by the relayer and sent with the message to the destination chain.
Exactly.
Yeah. Okay.
Yeah,
cool.
yeah. The relayer gets specifically all of the individual signatures from each of the validators and then produces the aggregated signature.
So from the destination chain's perspective, it's basically, it's not going and it's not aggregating the keys, the public keys itself and producing an aggregated public key and comparing that to the aggregated signature.
Mm-hmm.
It's taking the already produced aggregated public keys from the relayer and just checking that against the aggregated signature from the relayer.
Yes.
Okay, cool.
Mm-hmm.
I did have another question, if it's possible.
Yeah, it's fine.
So when there's like messages sent between the chains, is there any record anywhere where you can basically say like transaction X on this L1 sent this message to this other chain and triggered transaction Y on this chain?
So the relayer actually has logs for when the message was, when the aggregated signature was produced, and then when the message was sent and delivered on the destination chain.
Uh-huh.
The first part of that, where you said the transaction executed, will just be an on-chain transaction on the source chain. So I guess there isn't one single place where all of those steps exist, but the logs of the relayer actually have most of those, probably just not. It might say something like receive transaction and receive request to send message from L1B, but I don't think it has all the details of that transaction. Not in one place. It might have the transaction hash, but.
And then in the transaction on the destination chain, are you able to like backtrack it to the relayer message that was sent, if that makes sense? So
I think that the interface for the teleporter receiver includes the origin chain ID and the origin sender address. So you can use those credentials to backtrack it to the original chain.
Right, but not like a unique message ID to maybe I can give context.
Yeah.
So I work for Yieldjack. We're doing a new project called Tesseract using ICTT. Okay. I'm not like a Solidity developer or anything, but I'm on the analytics side. Mm-hmm. So I'm trying to like figure out how to piece together the information required to analyze it. Mm-hmm. So I want to be able to say like if we're doing something that is bridge swap bridge or whatever, I want to kind of like unify them and say these all happened as part of one, obviously not one transaction, but one action.
I see.
So I want to be able to say like,
So I actually don't know for sure if there's one single source where you can get all of that information, but we can ask Michael, and we would love to talk about that with you more. Yeah.
Thank you.
Yeah.
Thank you. I have a question more about the architecture of this overall cross-messaging system.
Sure.
The relayer, why is it not a P chain?
Why is the relay not in the P chain? Because it would just produce like extra load on the P chain, and it's not super necessary that the relayer act in conjunction with Avalanche Go. You can run multiple relayers. You can have, if you're actively sending transactions between multiple chains, a whole economy of relayers that compete for each message to earn some type of fee. But simply adding the relayer as a part of Avalanche Go would just produce a heavier load on like the networking aspects, and it would just slow down the P chain, which we didn't think was really something that was super necessary. Yeah. Any other questions? We have 30 seconds.
I
No, come on.
The clock is ticking. We gotta go.
okay. Okay. Can you tell us a couple of samples where this feature is used more than you showed a very simple sample with the number 2
Of
from one chain
course,
from
and I
another.
see that you're wearing a Chainlink shirt, so this one will really excite you. But there is CCIP, and there are Chainlink oracles as a service only deployed on the C chain. And a lot of L1s want to use the information they can get from Chainlink oracles, but Chainlink is not willing to deploy their whole service on their L1 because they have to manage that, right? So what they'll do is they'll set up one-way teleporter request contracts that they can request information from an oracle on Chainlink and just send it, warp it to their L1. So that's a really useful one. We also have ICM contracts has a multi-hop feature too. So if you want to use the C chain as like a place where you want to perform an action and then send it to another L1, you can actually have multi-chain hops with one call to one transaction. Okay. Yeah. One more question from him, and then they're going to kick me off.
It was such a coincidence. I wanted to ask you what's the main advantage over Chainlink CCIP? So
Chainlink CCIP is primarily L1 to L1, meaning more established networks. So Chainlink CCIP connects Avalanche with Ethereum and any other EVM chain, versus ICM contracts and ICM as a protocol is native and available to any chain launched within the Avalanche network. So that's the primary difference.
But the advantage, I wanted to know if there is a certain advantage.
We can get into that later.
Okay.
Yeah.
Cool.
All right.
Okay. Thank you very much.
Thank you very much. I have to cut it off now, but I'm willing to take your question off the stage.
In 30 minutes, you can learn how to integrate both of them.
Okay. Nice. There's going to be a presentation about integrating both CCIP and ICM contracts. Yes. All right. Thank you, everybody.